Hello everyone, this is Surajit and you are welcome to our channel. In this channel, we discuss different principles of physics and also we solve a wide range of numerical problems based on these principles. So in this video, we'll focus on calculating the electric field due to spherical symmetric charge distributions using Gauss law. Well, in last few lectures, we discuss different concept of electric field lines, their mathematical representation, their key properties. Later on also we have discussed the concept of electric flux and we have learned how to calculate electric flux for different cases. Particularly in last lecture we have talked about Gauss law, where we have noticed that in the statement of Gauss law it says that the electric flux through any closed surface is 1 by epsilon naught times charge enclosed by the closed surface. Well, this statement is valid for all kind of closed surface and all type of charge distribution. However, there is a misconception that Gauss law is valid for only symmetric charge distributions. This is not true. Gauss law is valid for all type of closed surface and all type of charge distributions. All type of charge distributions mean either it could be symmetric, it could be asymmetric, it could be a point charge, or it could be a continuous charge. All type of charge distributions Gauss law is valid. However, the symmetric charge distributions makes our mathematics easy in order to calculate the electric field for different kind of continuous charge distribution. So in this video, we will learn how to calculate electric field for spherical symmetric charge distribution using Gauss law. But before diving into the calculations of electric field due to spherical symmetric charge distribution, I would like to explain few important points that will help us to understand the beauty of Gauss law and as well as the beauty of symmetric charge distribution. So let's start, and first we'll talk about spherical symmetric charge distribution. So right here, spherical symmetric charge distribution. So here I am going to the idea that if examiner give you some charge distribution and he asks whether this charge is carrying spherical symmetric or not. So how we can do that? How we can argue that this charge distribution has spherical symmetry or this charge distribution doesn't has any spherical symmetry. Okay. So for that, first condition that charge should be distributed over the spherical region. Charge should be distributed over the spherical region. So first one right here, charge should be distributed. Charge should be distributed over a 1 minute please. Charge should be distributed over a spherical region. This is the first condition, and second condition, we want to know what could be the mathematical representation of the symmetric charge distribution. So for that, just let me draw a spherical region. Let's say this is a spherical region where charge is distributed in the spherical region. Okay. So this is the spherical region where some amount of charge is distributed. So now we want to see whether this charge has spherical symmetric or not. The first condition, charge should be distributed over the spherical region. So in this case, charge is distributed over the spherical region. Now we want to check whether this charge carries spherical symmetric or not. So in order to check whether this charge carries spherical symmetric or not, what we can do, we can just draw two concentric spherical surface like this. Spherical surface like this. So after drawing this spherical surface, what we have to do, we have to calculate electric field at this point. Sorry, not electric field, electric charge density. Consider, we have to find out what will be the charge density associated with the given charge distribution at this point, and then we'll also calculate the electric field at each point over this surface. On this surface, we'll calculate here, we'll calculate here, we'll calculate here, we'll calculate here, calculate here. Everywhere we'll calculate the charge density, and also we'll calculate the charge density on this surface, second surface, at every point. At every point. So after calculating charge density, we see that whatever charge density we are getting on this surface, let's say on the inner surface, if we get the same charge density at every point on this surface, that's mean here, 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 everywhere, whatever charge density we are getting here, if we get the same charge density at everywhere on this surface, then we can say this charge distribution has spherical symmetry. Now sometimes what happens, let's say if we calculate the charge density on the inner surface as well as on this surface, so on the individual surface, like whatever charge density we are getting on the inner surface at one point, if we get the same charge density on the at other point on this surface, and then if we calculate the charge density on this surface, second surface, and whatever charge density we are getting here, if we get the same charge density at every point on this surface, but this charge density may or may not be same. Like whatever charge density we are getting at each point on the first surface, and whatever charge density we are getting at each point on the second surface, they may be same, may not be same, but the charge density at each point at each point on the individual surface, that's mean on the inner surface and on the outer surface, that must be equal. Okay, so let me just clear this statement again. Whatever charge density we are getting at each point on the inner surface, they must be same, and whatever charge density we are getting outer surface, I mean on the second surface, if they are also same, but it is not necessary that the charge density on the inner surface and outer surface, they must be equal. They may be different, but whatever charge density you are getting at any point on the individual surface, if this charge density is same at every point on this individual surface, then this charge distribution is called spherical symmetry. Okay? Spherical symmetry. Now from the figure, one thing clear, if I calculate the charge density on the inner surface, let's say at this point, and then if I go this point and this point and this point, in order to carry the spherical symmetric, the charge density on this every point on this surface must be same, and at different point on this surface, the value of theta and phi is different, but charge density is same. So we can say that the charge density is independent of r and theta. R and theta. Okay, and then next, if I calculate the charge density on the first surface, and then if I calculate the charge density on the second surface, they may be same, may not be same. Then we can say this rho can be only function of r. If they're same, then it will be uniform, everywhere will be same. But if it is different, then since on these two surface the value of r is different, so we can say rho is function of r. Rho is function of r. Okay, so in order to carry the spherical symmetric, the charge density can be represented by a constant value, or if it is variable, then it could be function of, it can be function of r only, but it cannot be function of theta and phi. So second important point right here, charge distribution either can be constant or function of r only, where r is the radial distance from the center of the sphere, but it cannot be function of theta and phi. Okay, it cannot be function of theta or phi. Okay, so that's mean if I give you charge density like this, as rho equals to rho naught, which is uniform charge density, and this charge is distributed over a spherical region, then this charge has spherical symmetry. Now if I give you second charge distribution, which is look like this charge density is rho, and then 1 minus r divided by capital R, where r is the radius of the sphere, given sphere, and this small r is the distance from the center of the sphere. Since in this case rho is only function of r, so in this case, since rho is only function of r, so we can say that this charge has also spherical symmetric. This charge has also spherical symmetric. But if I give you a charge density like this is rho naught cos theta 1 minus r square divided by 2r square into sine phi. So now you see this rho is function of r as well as function of theta and phi. So this cannot have spherical symmetry. So this charge distribution doesn't execute spherical symmetry. So that's mean either rho can be constant or rho can be only function of r, but it cannot be function of theta and phi. So that is the simple way to understand the spherical symmetric charge distribution. Charge must be distributed over a spherical region, and then either it could be a constant or it could be a function of r only, but it cannot be function of theta and phi. Well, so now we have understood how to check spherical symmetry, whether any charge carries spherical symmetric or not. Now let's say we have a spherical symmetric charge distribution and we want to calculate electric field using Gauss law. So let's say this is a region where the charge is distributed and this charge distribution has spherical symmetry. Okay, this charge distribution has spherical symmetry. And spherical symmetry means this rho is function of r only in this case. Rho is function of r only. Now we want to calculate electric field due to this charge distribution using Gauss law. So then what is the statement of Gauss law? Let me just write first. So according to statement of Gauss law, we can write E dot ds is equals to 1 by epsilon naught q enclosed. Q enclosed. So in order to calculate this electric field using Gauss law, what we have to do? First we have to consider a closed surface, which we called Gaussian surface. Now the shape of the Gaussian surface depends on the symmetry, what kind of symmetric charge distributions we have. So in this case, we have a spherical symmetric charge distribution. So now in this case, what we have to do? We have to consider a spherical symmetric charge distributions. So basically Gaussian surface is a surface over which the electric field should be constant. So whenever we are going to calculate electric field due to symmetric charge distribution, we have to consider a electric field, Gaussian surface in a clever way, where we can see that the charge electric field on the surface everywhere is constant. So in this case, let's say we want to calculate electric field at this point, then what we have to do? We have to connect this point with the center of the given charge distribution, and then taking this as a radius, we can draw a concentric spherical surface like this. So this is our Gaussian surface in this case. Okay, this is our Gaussian surface in this case. Okay, let's say radius of this Gaussian surface is r. So once we draw this Gaussian surface, and then let's say if we assume the radius of this r of the Gaussian radius of the Gaussian surface is r, then immediately in the next step what we do, we simply replace this integration by this result E into 4 pi r square. E into 4 pi r square. Now that is the beauty. We are replacing a so complicated integration, surface integral, just a simple result without creating any second thought. Once we have checked that this is a spherical symmetric, this charge has spherical symmetric, and then we have drawn a spherical surface around this given charge distribution, and then if we assuming that the radius of the spherical surface Gaussian surface is r, then immediately without creating a second thought, we replace this surface integral by this by this result E into 4 pi r square. Well, when we replacing this integration by this result, actually we are assuming two important assumptions. So what are these two important assumptions? First of all, on the Gaussian surface, we are assuming that every point that electric field is always along the directions of area vector, that is along the radial direction. Along the radial direction. And second thing, we also assume that the every point on the surface electric field is constant. Magnitude of electric field is constant. Then only we can replace this integration by this result. If electric field is constant over the surface and they have if electric field and area vector are in same direction, so E dot ds will give you simply E into ds. Since E is constant over the surface, we can take it outside, and then ds will give you 4 pi r square. Ds will give you 4 pi r square. So before solving any problem, we have to justify these two assumptions. We have to justify these two assumptions that every point on this surface, Gaussian surface, electric field will be along radial direction, and the magnitude of electric field on this surface same. Will be same. So for that, let me just consider one point on this Gaussian surface. Let's say this point. Let's say this point. I want to see what will be the electric field at this point because of this spherical symmetric charge distribution. So what we can do, we can simply edit this point with the center of the given sphere, and then I am extending this line this way. Okay, extending line this way. So now what you can see, if we consider any point on this line, any point on this line, and around this point if I consider elementary volume, and whatever will charge will lies within this elementary volume, for that if I want to calculate electric field at this point, what will be the directions of electric field? Let's say at this moment assume that the charge density is positive, then whatever charge is here within this elementary volume, because of this charge the electric field at this point will be along this direction. If I consider elementary volume here, this will also create electric field along this direction. This will also create electric field along this direction, this direction, this direction. Okay. Now since charge has spherical symmetric, so if we draw a straight perpendicular line like this, and let's say this line is perpendicular bisector of this line, and then if we consider an elementary volume here, elementary volume here or elementary volume here, you see both the point, the distance of both the point from the center will be same. Center will be same. So because of that we can say if we consider an elementary volume here and same elementary volume here, both the point will have same charge. If we consider elementary volume here the amount of charge that will lies within this elementary volume. If we consider same elementary volume here, the amount of charge within this elementary volume will also be same, because this charge is carries a spherical symmetric. This charge is carrying a spherical symmetric, and the distance of these 2 points are same from the center. So at this point charge density, at this point charge density will be same. So if we consider same elementary volume, then a charge within this elementary volume here or here, they will also be same. Now if I want to calculate electric field due to these two, the charge that is lies within this elementary volume, this will create an electric field at this point along this direction. And the charge that is lies the same elementary volume at this point, this will create electric field along this direction. Now you see, these two distances are also fixed, same in this case. Since this distance are same, so the distance of this point from the point where we are calculating electric field, this distance and this distance, they will also be same. And at these two positions, we have considered same elementary volume, so they will carry same charge. So if they carry same charge, then the electric field, magnitude of electric field at this point, because of this elementary volume, will be same. So, and the directions of them, the directions of the electric field because of these two charges will be like this. Now if I decompose this electric field, so one component will go along this direction, another component will go along this direction. Same way, if I decompose this electric field, one component will go along this direction, another component will go this direction. Now since these two electric field, magnitude of these two electric field are same, and you can say from the figure, this angle will be same, so this angle will also be same. So this component and this component will be cancelled out. Only net electric field will be along radial direction. Okay, so that's mean we can consider each point on the sphere like in the same pattern, and we can show you that the net electric field at this point will be radially outward direction. Radially outward direction. So not only this point, if we consider any other point on the Gaussian surface, using the same concept, whatever we have used here, you can justify that the electric field at every point on the Gaussian surface will be radial direction. Radial direction only. Okay, so first assumption is justified that electric field on the Gaussian, if charge distributions carries a spherical symmetric, then everywhere on the Gaussian surface electric field will have only radial component. The radial component, either it will be, if the enclosed charge is positive, then it will be radial outward. If enclosed charge is negative, then it will be radially inward. Okay. Now second important assumption, we have also assumed that the magnitude of electric field at every point will be same. Every point will be same. You see, the way we have calculated electric field here, because of this charge distribution, if I consider another point here, what we'll see here, one moment. So if we consider another point here, and if we connect this point with the center of the given charge sphere, and then extend like this, so you will see whatever charge distribution this observer will observe, the observer who is sitting here, he will also see the same charge distributions at the same distance, because this charge distribution has spherical symmetric. So now if I draw a line like this, so at this point and this point, if this distance is fixed, this distance are same, whatever distance here, this distance and this distance, if this distance are same, then the charge density at this point will be also same. So whatever we'll consider point here, like here, same way if we consider a 2 point here, we'll got also the same charge distribution. So because of that, the observer who is measuring electric field here, the observer who is sitting here, he will also see the same charge distributions at the same distance. So if two observers will observe the same charge distributions at a same distance, then what will happen? whatever electric field this observer will measure, the same the observer and the whatever electric field second observer will measure, their magnitude will also be constant. You see, if I have a charge distribution like this, and if we have a similar charge distribution like this, now if I put a one observer here, and then if I put another observer here, if this charge distribution, whatever charge distribution here, if this observer see the charge distribution, certain charge distribution at a certain distance, and if the same charge distributions also has been noticed by this observer, if this observer is also see the same charge distributions, mean at a same distance, same amount of charge is distributed over this surface, over this volume, then in this case, whatever this observer will measure the electric field, and whatever this observer will measure the electric field at this point, their magnitude will be same. Their magnitude will be same, because electric field, ultimately the magnitude of electric field will be depends on only charge distribution and the distance between source point and the observer field point. So in this case, if this observer see the same charge distributions at same distance, at certain distance, and the second observer is also observe the same charge distribution at the same distance as the first observer is observing, so both the observer will measure electric field with same amplitude, with equal magnitude. So in this case, if charge distributions carries a spherical symmetry, so the observer who is sitting here, or if we put another observer on the surface, n number of observer in the surface, you'll see each observer will observe the same charge distribution at the same distance, and because of that, the electric field, the magnitude of electric field on the Gaussian surface everywhere will be same. Everywhere will be same. So now both the points are justified that why this electric field, magnitude of electric field will be same over the Gaussian surface, and everywhere the electric field will be along the radial direction. Everywhere it will be along radial direction. If it is positive charge, then it will be radial outward. If it is negative charge, then it will be inward. But in calculations, we always assume that the electric field will be always radial outward. That's why it is written as a positive. You see, if the charge enclosed charge, if this charge density is positive, then this enclosed charge will also be positive. So we'll get electric field positive value, and then we'll simply multiply with the what is the directions of area. That the directions of area is r cap. So electric field will also be along r cap. But if we get a negative enclosed charge, but this side will always write a positive, so automatically what we'll get a negative electric field, because enclosed charge is negative. So in this case, electric field will be radially inward direction. Electric field will be along minus r cap direction. Okay, so positive charge, negative charge, just the directions of electric field, make the directions of electric field reverse. If it is positive charge, then it will be radial outward, but if negative charge, it will be inward. But if this charge is spherically symmetric, then that electric field on the Gaussian surface everywhere, it will be radial direction only. It will not have any other component like phi component, theta component, any other component. It will only have r component in this case. Okay, and then what we have to do in right side, we have to calculate whatever the enclosed charge within this Gaussian surface. So for that, what we do, whatever the charge density will be given in the questions, we have to integrate this charge density over the volume of the Gaussian surface, and for that we just multiply these two things first, charge density and the elementary volume in spherical polar coordinate r square sine theta dr d theta d phi, and then we have to integrate over this volume of within the volume of the Gaussian surface, within the volume of the Gaussian surface. So in this case, radius of Gaussian surface will be 0 to r, theta will be 0 to phi, and phi will be 0 to phi. Okay. But you see, we have to integrate this rho over this volume, and since this charge has spherical symmetric, so it will be only function of r. So for symmetric charge distribution, this integration will be always in this integration always theta dependent term will be sine theta d theta, and phi dependent term will be d phi. There will be no other term associated with theta and phi. So that's mean if charge distributions are spherical symmetric, then this sine theta term will be always theta term will be always sin theta d theta, and phi term will be always d phi. And for spherical symmetric, we will consider a Gaussian surface like this, complete spherical surface. So in this case, if we integrate this value, this will give you 2 and phi will give you 2 pi. So this sin theta term and phi term together will give you 4 pi. So from next time, if we want to calculate enclosed charge within Gaussian surface for symmetric charge distribution, we will replace this elementary volume in this way, rho, and then elementary volume will replace like this way, 2 pi 4 pi r square into dr. That's mean we are putting this elementary volume after calculating the theta term and phi term over the surface, because this rho will be independent of theta and phi. So this integration will be always like for theta term, and the contribution of theta term and phi term together always give us 4 pi. So only this r dependent term will be different for different value of rho, and then we have to integrate like this. Okay. Yep. So these are few important points. If you know this term, and then I think it will be super easy to calculations of electric field due to symmetric charge distribution. Okay. So now see how we can calculate electric field using this law for different kind of spherical symmetric charge distribution. So first write here electric field inside and outside due to a uniformly charged carrying sphere. Okay. So first problem is here. We want to calculate electric field inside and outside due to a uniformly charged carrying sphere. So let me draw a figure first. Let's say we have a sphere like this, and radius of this sphere, let's say capital R. Okay, radius of this sphere is capital R, and this charge carries a uniform charge density. That's mean at everywhere inside the volume charge density is same. Charge density is same. So that's mean rho is equals to rho naught. Okay. So before solving the electric field using Gauss law, you have to check whether this charge has spherical symmetric or not. So now, as we have noticed here, in order to be these charge distributions will qualified or will carry a spherical symmetric charge distribution, for the first condition, charge should be distributed over a spherical region. So here you can see charge is distributed over the spherical region, over the volume of sphere radius r. Second, either it will be constant or it will be a function of r only. So in this case, it's a uniform, means constant over this volume. That's mean this charge has spherical symmetry. So we can use Gauss law in order to calculate electric field due to this charge. Okay. So now if I want to calculate electric field, so first we have to consider a point where we want to calculate electric field. So we want to calculate electric field inside the sphere. So right here for inside point. Inside point means where the charge is distributed over the volume of a sphere of radius r, and we want to calculate at any point inside the sphere. So for that, let's say this is an arbitrary point. We want inside the sphere, we want to calculate electric field at this point. Okay. So if we want to calculate electric field at this point using Gauss law, what we have to do? First, we have to connect this point with the center. Since charge distributions has spherical symmetric, so in order to calculate electric field due to using Gauss law, what we have to do, we have to draw a Gaussian surface concentric with a given charge distribution, taking this distance as a radius of the Gaussian surface. Okay, so let me draw a Gaussian surface like this in this case. Okay. This is our Gaussian surface. Now, since charge is spherical symmetric, so everywhere on the Gaussian surface electric field will be radially outward direction, and the magnitude of electric field on the surface will be same. So now if the electric field, the magnitude of electric field on the surface, let's say E, then what we can write according to statement of Gauss law, E dot ds is equals to 1 by epsilon naught q enclosed, q enclosed by this Gaussian surface. And then immediately next step what we'll do, since the given charge distributions has spherical symmetry, so we'll simply replace this integration E into 4 pi r square. But this is for only spherical symmetric charge distributions. Later, maybe next class we'll talk about cylindrical symmetric and then plane symmetric. For different cases we have to replace this integration for different value. So for spherical symmetric, we'll always replace this E into 4 pi r square, where r is the radius of the Gaussian surface. This equals to what we have to do on the right side, we have to calculate the enclosed charge. So for enclosed charge, what we have to do, whatever the charge density is given, we'll put the value of charge density, and then we'll write the elementary volume in this way, 4 pi r square into dr. And then we have to integrate up to the Gaussian surface. So 0 to r. So that is the enclosed charge within the surface in this region. This will be the volume that is enclosed by the Gaussian surface. So we have to calculate what will be charged within this Gaussian surface. So in this case, the limit will be 0 to smaller. 0 to smaller. So what will give this integration? Rho in this case uniform everywhere same, so you can take it outside. Then 4 pi is also constant, you can take it outside. Then r square, integration of r square will be r cube divided by 3, and then lower limit is 0, upper limit is smaller. So finally what we'll get, you will get a 4 pi rho naught r cube divided by 3 epsilon naught. 3 epsilon naught. Now if I divided 4 pi on the right side, if we divide it by 4 pi on the right side, or simply on the both side, then what we'll get E is equals to 4 pi will cancel out, and r square will also cancel out from both sides. Then what we'll get, you will get rho naught r divided by 3 epsilon naught. Rho naught r 3 epsilon. Now finally we are getting a positive value of r. So in this case, if I want to write in vector form, then what we'll do, we'll simply put a r cap here. Okay. As we have already noticed that if the charge distributions has spherical symmetric, then it will have only r components. So if we get positive value magnitude of this electric field, then it will be rho r divided by 3 epsilon r cap. If we get negative value of electric field, then we'll simply it will be minus r cap direction. Okay. So this is the electric field at any point inside the sphere at a distance r from the center of the given charge distribution. Center of the given charge distribution. So when we talk about inside point, that's mean in this case the value of small r will be less than capital R. Less than capital R. Now we are also interested to calculate electric field outside the sphere. Outside the sphere. So next right here, electric field outside the sphere. So for outside point. For outside point. So now we are interested to calculate electric field outside this sphere at any point outside this region. So for that I can consider a arbitrary point here. Let's say we want to calculate electric field at this point. Then what we have to do, since this charge distribution has spherical symmetric, so we want to use Gauss law. So if we want to use Gauss law, then first step what we have to do, we have to connect this point with the center of the given charge distributed sphere, given sphere, and then taking this distance as a r, that is the radius of a spherical surface, we have to draw a concentric spherical surface with the given charge distribution. So we can draw like this. Draw like this. So this will be the spherical Gaussian surface. We want to calculate electric field on this Gaussian surface. Since charge distribution is spherical symmetric, so everywhere on this surface again magnitude of the electric field will be same. Now if we assume that on this surface electric field is E, so according to this Gauss statement, what we can write, I can just write the statement first. E dot ds is equals to 1 by epsilon naught q enclosed. And then next step what we'll do, we'll simply replace this E into 4 pi r square. And now we have to find out enclosed charge within this Gaussian surface. Since we have considered this point outside this given charge distribution, so in this case this enclosed charge means it's an enclosed charge within the Gaussian surface. However, this charge is distributed up to capital R. From capital R to this Gaussian surface, up this region there is no charge. So in this case, what will be the limit of this R dependent term? Volume charge density is uniform rho, and then 4 pi r square, that is the elementary volume, and dr, then we have to put the limit in order to calculate total enclosed charge within the Gaussian surface. I mean, we have to calculate enclosed charge from here within this region from 0 to smaller to this volume. But since charge is distributed up to capital R only, so what we'll write, we can decompose this limit, say 0 to small r is equals to 0 to capital R plus capital R to small r. But in this case, capital R to small r, there will be no charge, so this term will be 0. So ultimately total enclosed charge within the Gaussian surface will be rho naught into 0 to capital R. 0 to capital R. So when we'll do this integration, finally what we'll get 4 pi rho naught and then capital R cube divided by 3 epsilon naught. 3 epsilon naught. And then if we divided this 4 pi r square on the right side, then what we'll get E is equals to rho naught r cube divided by 3 epsilon naught r square. 3 epsilon naught r square. So again we are getting positive value. So if we want to write vector form, then what we'll do, we'll simply multiply with r cap. This will be the directions of electric field on the surface at any point. Okay, and this is the magnitude of the electric field. Okay, so now take a look the variations of electric field inside point and outside point due to a uniformly charge carrying sphere. And also I will request you, I mean, if you are preparing for any kind of competitive exam, then I will again request you just to remember this final result, because using this result also we can solve different, I mean, at least 4 or 5 different type of questions. So if this charge is carrying a uniform charge density, a sphere is carrying uniform charge density or charge density, let's say rho naught, then inside at any point at a distance r from the center, electric field will be rho r divided by 3 epsilon naught. If this charge density is positive, then electric field will be along r cap. It is negative, then it will be minus r cap. And on the outside, it will be rho r cube divided by 3 epsilon naught r square. R square. And so if we want to draw a variations of electric field with respect to r, that is distance from the center of the charge carrying sphere, what we'll see, up to r is equals to capital R. Let's say on the y-axis we are writing electric field, on the x-axis we are writing the value of r, that is the distance of the point from the center of the sphere. So in this case, what we'll see, when this r is less than capital R, and for outside point means this r is greater than capital R. So in this case, what you will notice, at r equals to 0, I mean 0 to capital R, electric field will be varies like this, will vary like this. U will be proportional to R. So at r equals to 0, electric field will be 0, and then as you will increase the value of R, electric field will increase up to capital R. As soon as you will cross the surface r equals to capital R, then you will lie actually outside the spherical surface. So when you are outside the spherical surface, then electric field will vary like this. So now electric field will fall with the R. As R will increase, electric field will fall 1 by R square. So outside electric field is inversely proportional to the square of the distance from the center of the sphere. So then electric field on the outside, it will be fall like this, 1 by R square. Okay. Inside it will increase with the R, outside it will decrease as 1 by R square. Okay. And so from here also we can sometimes, as I told you, that we are not only just here to understand the idea, we are also want to solve a number of numerical problems. So sometimes, examiner give you a simple problem. If we have a spherical symmetric charge distribution, and if the charge density is proportional to r to the power n. So if we have a spherical symmetric charge distribution, then charge density will be only function of r. So in this case, if charge density is only function of r, and if total charge on the spherical region, over the spherical region where charge is distributed, if the total charge is non-zero, then what will be the variations of electric field inside the spherical region and outside the spherical region? Outside the spherical region. So in this case, you see, if the charge density is proportional to r to the power n, and if the total charge is non-zero, then inside this surface, electric field will be always proportional to r to the power n plus 1. R to the power n plus 1. And outside, if total charge is non-zero, then at outside electric field will be always it will be always function of 1 by r square. So inside, if rho is proportional to r to the power n, then inside the sphere, electric field will be proportional to r to the power n plus 1. And outside, it will be always inversely proportional to the square of the distance, the point from the center of the sphere. Okay, so that's mean if r is proportional to, say rho is proportional to r cube, then inside electric field will be r to the power 4. Electric field proportional to r to the power 4, and outside it will be always 1 by r square. But for that, total charge should be non-zero. If total charge is 0, then outside electric field will also be 0. There will be no variations of electric field. Okay. So these are some important points associated with the uniform charge distribution, and I hope also you understood how we can calculate electric field using Gauss law. Now, instead of uniform charge distribution, if we have some kind of non-uniform charge distributions, but if this charge distribution has spherical symmetric, then it will be only function of some rho naught r square r cube or some function of r. Then what will be the changes of this problem? Only you have to replace this rho naught by this, whatever the rho is given here, you have to replace that rho, and then you have to integrate with respect to r. Or same here also, you have to replace this rho naught by the given charge distribution, and then you have to integrate, and then finally you get the electric field. So I hope you can do that. Okay, so now next we will learn how to calculate electric field due to a uniformly charged carrying spherical cell. Uniformly charged carrying spherical cell. So right here, electric field due to electric field inside and outside due to a uniformly charge carrying charge carrying spherical cell. Charge carrying spherical cell. So here we have calculate electric field inside and outside due to a uniformly charge carrying sphere. That means charge is distributed over the volume. Charge was distributed over the volume in this case. In second case, we are assuming a charge carrying spherical cell, but in this case charge is uniform. That's mean now, since it is a spherical cell, so charge will be distributed over the surface only, and it is uniform means every point on the surface will be constant. Let's say this is our spherical cell of radius r. Now charge is distributed uniformly over its surface. So that's mean we have surface charge density, and in this case surface charge means charge per unit area, and that is uniform means everywhere it's constant. Rho naught. Sigma naught. Sigma is equals to sigma naught. That is the charge distribution. So again you see the charge is distributed over the spherical surface. Spherical surface, and everywhere here everywhere, since sigma is sigma naught, so everywhere it is constant. So again we can calculate electric field using Gauss law. So now in order to calculate electric field using Gauss law, what we have to do? First we have to consider a point in a region where we are interested to calculate electric field. So in this case, first we want to calculate electric field inside this spherical cell. So for that, consider a point inside the spherical cell. So let's say this is the point. We want to calculate electric field at this point. So if we want to use Gauss law, then what we have to do? First we have to connect this point with the center of the given spherical cell, and then taking this distance as a radius, and we have to draw a concentric spherical surface with the given charge spherical cell. So in this case we can draw like this. So this is our Gaussian surface, and then if on the surface electric field is E, so let me just write here for inside point, that is the point we have considered here, P at distance is R, so this R is less than capital R. So now we want to calculate electric field at this point. So for that we have drawn a Gaussian surface, and then we assume that the electric field on this Gaussian surface is E. So according to the statement of Gauss law, E dot ds is equals to 1 by epsilon naught q enclosed, 1 by epsilon naught q enclosed, and then in this case again we'll write E into 4 pi r square. This is equals to, what will be the enclosed charge? So in this case charge is lies on the surface on the spherical cell. So what will be the enclosed charge within this Gaussian surface? It will be 0. So enclosed charge is 0. So if enclosed charge is 0, then what will be the value of electric field? So you see enclosed charge is 0. That simply suggests that the total surface integral will be 0. Now the surface integral can be 0 because of two reasons. First of all, at every point, it may be happen that the electric field at every point will be perpendicular to the surface. Perpendicular to the surface. At every point, at this point, electric field will be perpendicular to the surface. Then only E dot ds will also be 0. Or it may be happen that the every point, everywhere, this electric field will be radial directions, but the magnitude of electric field is 0. Magnitude of electric field is 0. If everywhere the electric field is 0, then also we see that this surface integral will also be 0. surface integral will be 0. So how we can justify that the every point, everywhere, this electric field will be 0? There is two conditions. This we are getting actually enclosed charge 0. That simply suggests that the total surface integral will be 0. Now there is two possibilities that everywhere electric field can be normal to the surface. So because of that, everywhere E dot ds is equals to 0, and that's why we are getting 0. Or let's say electric field and everywhere on the surface, electric magnitude of electric field is 0. Because of that, actually we are getting 0. We are getting 0. So already we have discussed here, if charge distributions has spherical symmetric, it doesn't matter you are taking outside point or inside point, everywhere electric field will be always radial direction. So in this case also charge distributions has spherical symmetric, so everywhere electric field will be radial direction. If it is non-zero, then it will be along radial direction. So that's mean first condition is not correct, that electric field will be normal to the surface. Electric field will be always radial directions, meaning it will be along the direction of electric field if it is non-zero. Then we have only one possibility, is that electric field will be 0 at every point. Electric field is 0 at every point. And I think that we can also easily understood how this electric field will be 0 at every point inside the spherical surface, I mean uniformly charged carrying sphere. So for that, what you can do, you just draw a spherical surface like this. This is carrying a uniform surface charge density, and then consider any point inside the spherical region like this. Yeah. And then we can draw a pair of cone which will passing through this point in this way. Let me just do it. This way. So let's say this is a cone, pair of cone, it's two cone, this one and this one. So let me use two colors. This is the one cone and this is the another cone. So we draw a pair of cone. This is connected at this point. Connected at this point. So now if the flat area on this cone, let's say if this is ds1, I mean that is ds1, and this area is, let's say, ds2. And let's say perpendicular distance of this area s1 from the point where the two cones actually intersect with each other, r1, and the perpendicular distance of this surface from this point, let's say r2. R2. And since this surface is carrying a uniform charge density and surface charge density is rho, so according to Coulomb's law, instead of using Gauss law, if I just calculate electric field using Coulomb's law, because Coulomb's law is valid for all type of charge distribution. So if I want to calculate electric field at this point because of this two cone only, then let's say electric field because of this charge on this elementary area ds1 is E1, and for that electric field will be K by 1 by 4 pi epsilon naught. And then according to Gauss law, Coulomb's law, the charge on the elementary area, so sigma naught into ds1 divided by the perpendicular distance of this surface from this point, so that will be r1 square. R1 square. And same way, if I want to calculate electric field at this point because of this second elementary area ds2 area, so if this electric field is E2, then what will be the magnitude of E2? It will be 1 by 4 pi epsilon naught, and then sigma naught, and then this area is ds2, so ds2 and the distance of this area from the point where we want to calculate electric field, that is r2, so r2 square. Okay, r2 square. So now if you see these two part, ds divided by ds1 divided by r1 square and ds2 divided by r2 square, this is actually called solid angle. Solid angle. So if we draw a cone like this, if we draw a cone like this, if this surface area, let's say ds, and the distance of the vertices from this surface, perpendicular distance, if this distance is r, then the solid angle, that area is created at this point, the solid angle is defined as d omega is equals to ds divided by r square. ds divided by r square. So in this case, you see from this figure, we can say that whatever the area, this ds1 area will create some solid angle here, and same amount of solid angle will also be created by this ds2 area. ds2 area. For ds1, the area of this portions is less, but the distance of the area from this center, from the vertices of the cone, is also less. For second case, area is large, but in this case, the distance of the vertices from this area is also large. So because of that, the ratio of these two quantity for both the cases will be same. So both the cases, they will creating a same solid angle. From this figure, it is clear. And so when these two solid angle are same, then we can say that the magnitude of electric field E1 and E2 at this point will also be same, because 1 by 4 pi epsilon naught is constant, sigma naught, they are constant, and now these two term is also same solid angle. So electric field at this point will be same, and the electric field because of this portion will be downward, and electric field at this portion will be upward, and they will cancel out each other. They will cancel out each other. So in the same way, all other part of the sphere, can be represented by a large number of pair of cone like this, and every time this cone will passes through this point, pair will passes through this point. Let me just draw another cone. Like this. So now this area and this area, so they will, you see, they will also create a same solid angle, maybe different from there, but whatever they will create, these two pair of solid angle, their pair of cone will create same solid angle. They will also create same electric field here, and they will cancel out with each other. So similarly, whole surface of the sphere can be represented by a large number of pair of cone in this way, which will passes through this point, and every time each pair will create a net electric field 0, and because of that, the electric field at this point will be 0. Since this is true for this point, this can be also true for any other point inside the spherical region. So in this way, we can say that the electric field inside the uniform charge carrying sphere will be 0. So in this case, electric field at every point on this uniformly charge carrying spherical cell will be 0. Everywhere it will be 0. Now if we want to calculate electric field outside the sphere, so now here, right here, for outside point, so for that, what we have to do, we have to consider a point that is outside the spherical, which lies outside the spherical cell. So at this point, let's say this point, we want to calculate electric field. So next step, what we have to do, we have to connect this point with the center of the spherical cell, and then taking this distance as a radius, we have to draw a Gaussian spherical surface like this. And then if we assume that the electric field on this surface is E, then according to statement of Gauss law, we can write E dot ds is equals to 1 by epsilon naught q enclosed. So in this case, again, we'll write left side, we'll write E into 4 pi r square And right side, what will write? We will write 1 by epsilon naught q enclosed. In this case, charge is distributed over the surface, and everywhere charge is constant, so total enclosed charge will be sigma naught into 4 pi capital R square. 4 pi capital R square. So finally, what we'll get electric field is equals to so if we write total charge is q naught is sigma naught into 4 pi R square, that will give you total charge. So total charge is q, then it will be q divided by 4 pi epsilon naught R square. So if total charge is q, then it will be q divided by 4 pi epsilon R square, where q is equal to sigma naught 4 pi R square, where sigma naught is the spherical uniform charge distribution. Okay. And what will be the direction? Since we are getting positive value, so it will be along marker. So inside will be 0 and outside will be q divided by 4 pi epsilon naught square. So if we want to draw the variations of electric field with the distance, then up to capital R, that is inside the spherical cell, electric field will be 0, electric field will be 0, 0, and then when you go outside, then electric field will start fall like 1 by R square. Okay, so this will be the variations of electric field. Inside 0 and outside it will vary. Electric field will be proportional to inversely proportional to square of the distance from the center of the sphere. So it will vary like 1 by R square. Okay, so this is the electric field inside and outside due to a uniformly charged carrying spherical cell. Spherical cell. Now let's consider a case like this. Instead of charge carrying solid sphere, we have a, so still now we have calculated two cases. One cases we have considered a uniform charge carrying sphere where the charge is distributed over the volume. Second case, we have considered a thin spherical cell where charge is distributed only over the surface. Now what we are interested to calculate, we want to calculate electric field due to a thick spherical cell. Thick spherical cell means it will have two radius, inner radius and outer radius, and we want to calculate electric field at different region. So let me just draw first figure. Let's say we have a spherical surface like this. We have a spherical surface like this where the inner radius is r and charge is distributed in this region. Inner radius, let's say r1, okay, and outer radius is r2. Inner radius is r1, outer radius is r2, and there is no charge in this region 0 to capital R1, and there is also no charge when r is greater than capital R2. So charge is only distributed over the region R1 and R2 in this region. And let's say this charge density is uniform. Again, it could be function of r. So if it is function of r, then you have to replace this r naught by the whatever value to be given. So just for simple calculations, let me just assume that in this case rho is uniform. If it is non-uniform, then whatever we are doing here, whatever mathematics will do here, you have to do the same thing, only you have to replace rho naught, whatever the function it will given in the question. Okay. So right here, electric field due to a electric field due to a uniformly charge carrying thick spherical cell. Thick spherical cell. So in last problem we have solved electric field inside and outside due to a thin spherical cell. There's only one radius. Now it has two radius. Inner radius is R1 and outer radius R2. So there is some portion, there is some volume between R1 and R2, and in this region charge is distributed uniformly. And we want to calculate electric field at different points. Let's say R less than R1, R1 and R2, between R1 and R2, and R greater than R2. Okay. Okay. So first write for R less than R1. So in this region, if we want to calculate electric field, then how we can calculate electric field? So this is R1 surface. So within this region, if we want to calculate electric field, how we can calculate that electric field? So for that, what we have to do? First, consider a point in this region. Let's say this is the point, and then we have to connect this point with the center of the sphere, spherical cell in this case. And then taking this as a radius, we have to draw a concentric spherical Gaussian surface. So this is the concentric spherical Gaussian surface. And now on this surface, if the magnitude of electric field is E, magnitude of electric field E, then according to Gauss statement, what we can write? We can write here E dot ds. E dot ds is equals to 1 by epsilon naught Q enclosed. Q enclosed. Now in this case, Q enclosed is 0. There will be no enclosed charge. So as we have noticed for symmetric, in last problem, so charge is spherically symmetric and there is no charge within the Gaussian surface. So in this case, electric field at every point will be 0 in this region. So electric field will be 0 in this case, in this region. Okay, so when R is less than R1 in this region, everywhere electric field will be 0. Then for the second case or second region, for R less than capital R2 but greater than capital R1. So that is from this surface to this surface. So between these two surfaces, if we want to calculate at any point electric field, what will be the electric field? So for that, again, let me consider a point over there. Let's say in this region, consider a point here. Let's say this is the point. Then what we have to do, we have to connect this point with the radius of the center of the given sphere or given spherical cell. And then taking this distance as a radius, we have to draw a concentric Gaussian surface like this. So this is our Gaussian surface now. So now if we assume that the electric field on this surface is Z, then according to statement of Gauss law, again we can write E dot ds is equals to 1 by epsilon naught Q enclosed, 1 by epsilon naught Q enclosed, and then E dot ds we can write here E into 4 pi r square, because over this charges has spherical symmetric. So over the surface everywhere electric field will be same, magnitude of electric field will be same, and it will be along the directions of area. So it will be E into 4 pi r square. And then enclosed charge 1 by epsilon naught. So now we have some finite amount of charge distribution within this volume. So we have to calculate what will be the enclosed charge. So for that, what we put? First we have to put the value of rho. In this case, rho is rho naught. And then elementary volume, we'll write 4 pi r square into dr. Now we have to calculate actually enclosed charge within the Gaussian surface. So Gaussian radius of the Gaussian surface is actually smaller, 0 to smaller. But you see 0 to R1 there is no charge. So we have to calculate what is the charge between R1 and Gaussian surface. So in this case, we'll put the limit R1 to R1 to R. So when we'll do that, and then if you do the integration, what we'll get here, we'll get 4 pi rho naught by epsilon naught 4 pi rho naught by epsilon naught, 4 pi rho naught divided by epsilon naught, and then this integration of r square will give you r cube. So small r cube minus r1 cube divided by 3. And then if we divided the 4 pi r square on the right side, so finally what we'll get E is equals to rho naught divided by 3 epsilon naught, and then r minus r1 cube divided by r square divided by r square. Okay, so this is the magnitude of electric field in this region, and then directions of electric field will be along r cap direction. R cap direction. Okay, so this is the electric field between this region r1 and r2, and now we want to calculate electric field in this region when r is greater than capital R2. So now we are looking for electric field in this region when r is greater than R2. R is greater than R2. So again, for that what we have to do, so this is the surface of R2, then we have to consider a point outside this surface. So this is the point, let's say, and then we have to connect this point with the center of the given spherical cell, and taking this distance as a radius, we have to draw another concentric Gaussian surface like this. So now we have to, what if we assume that the electric field on this Gaussian surface is E, then again according to the statement of Gauss law, what we can write? We can write E dot ds is equals to 1 by epsilon naught q enclosed, 1 by epsilon naught q enclosed, and then next step we'll write E into 4 pi r square. Now what will be the enclosed charge? So we have to calculate the enclosed charge within the Gaussian surface, that is 0 to smaller up to this point, but this in this case charge is distributed within r1 to r2. So we can actually break this limit for this surface 0 to r. Now we can break this limit 0 to r1 plus r1 to r2 plus r2 to r. But you see in this region there is no charge, rho is 0, so this will also give you enclosed charge 0. r2 to r1 in this region there are also no charge, so this term will also give you 0. Only you will get non-zero for this region r1 to r2. So what we'll write here? We'll write here simply 1 by epsilon naught and then volume charge density rho naught into 4 pi r square dr, and in this case limit will put r1 to r2. R1 to r2. So after calculating this integration, what we'll get? We'll get 4 pi rho naught divided by 3 epsilon naught, and then r2 cube minus r1 cube. R2 cube minus r1 cube. So then if you divided this 4 pi r square on the right side, if we divided this 4 pi r square on the right side, what we'll get? We'll get E is equals to rho naught divided by 3 epsilon naught r2 cube minus r1 cube divided by r square. Divided by r square. So in this case also electric field will be readily radial direction, so we can written as rho by 3 epsilon naught r2 cube minus r1 cube divided by r square into r cap. Okay, so this is the variations of electric field at different region for the case of thick spherical cells, which is carrying the uniform volume charge density. But sometimes if examiner give you a non-uniform charge density, but if this charge distributions carry a spherical symmetric, that means rho will be function of some function of r. So what we have to do then, you have to just replace this integration where we have put it here rho, you have to replace this rho not by this sum, whatever value will be given in the exam. And same way here also, you have to replace this rho naught, whatever the value was given by the examiner, put that, and then you have to integrate between r1 and r2, and that will give you the enclosed charge. And then from there you can also calculate electric field for other cases. For uniform cases, this electric field will be like this. Inside will be 0, outside between this region r1 r2 it will varies like this, and then outside it will also varies like this. So for again, if we want to see the variations of electric field graphically, then we can represent this way. Let's say y-axis we are writing electric field, value of electric field. On the x-axis we are writing value of r, that is distance of the point from the center of the thick spherical cell. So in this case, let me mark 2 points. One is r is equals to r1, another is r equals to r2. So you see up to r1 electric field will be 0. R1 there will be no electric field. Inside electric field is 0. Now between r1 and r2 it will varies like this. So when r1 is just greater than this r is just greater than r1, just greater than r1, but it's very small. So in this case this term will be dominating. This term will dominate. So in this case it will this electric field will increase linearly, and then as we increase the value of r, then this term will come to this term will also try to dominate. Then finally you will see the electric field variations almost like initially it will be increased straight line, and then as we increase the r, this term, when you value increase the r, this term will also decrease because it is 1 by r square and it is negative sign. So effectively ultimately electric field will increase, but it will increase more rapidly. So initially it will be straight line, and then later it will be more like this. And then when you cross r2, so outside you see it will be electric field will be electric field will varies like 1 by r square. So electric field will start decrease with the distance as 1 by r square. So it will be fall like this. Electric field will falls like 1 by r square. Okay, so this will be the variations of electric field for different cases. Up to r1 0, r1 r2 it will increase like this, and then greater than r2 it will decrease like this. Okay, so these are the different cases, and then I would like to solve one more important problem. Let's say we have already calculated electric field due to a uniformly charged carrying sphere, and using this concept we can also calculate electric field for this type of charge carrying sphere. But if it is not uniform to some function of r, then we have to just replace this rho naught by this given charge density, and from there we can calculate what will be the electric field at inside and as well as outside point. However, if we have a uniformly charged carrying sphere, and if we make some cavity inside this charge carrying sphere, and then if we want to calculate inside the cavity or resultant electric field outside the sphere with this cavity, how we can calculate this electric field. So again, let me first draw the figure of the given situation. Let's say we have a spherical region like this. Spherical region like this. Let's have radius r, and then charge is distributed over the volume of this sphere, and in this case also I am assuming that the charge is uniformly distributed, so everywhere charge density is same. Everywhere charge density is same. So now if we want to calculate electric field inside and outside, since charge is distributed over the spherical volume and it is uniform, everywhere is same, so we can use actually Gauss law and we can calculate electric field, and we already calculated electric field because of this type of symmetric charge distribution. So now the problem is, if we remove if we create a spherical cavity, within this charge carrying sphere. Spherical cavity means if we make a cavity where there is no charge, other point there is a charge, but we are creating a spherical cavity, that means where there will be no charge. So let me draw in this way. So let's say this is the spherical cavity, and inside the spherical cavity there is no charge. So remove this charge in this region. Okay, so we have a spherical cavity like this. Spherical cavity like this, where the center of the charge carrying sphere, let's say O, and center of the cavity, let's say O dash. O dash. Now we want to calculate electric field within this cavity, or if we want to also calculate electric field any outside point here or here, or we can calculate electric field. Yeah. So when there is no cavity, then everywhere charge is, within this volume everywhere charge is fixed. In this case also charge density is rho naught, uniformly charge carrying sphere. So everywhere charge is fixed and charge is distributed over the volume, so we can use the Gauss law. But as soon as we'll remove this, we create this cavity, we make this cavity within this charge carrying sphere. That's mean we are actually removing this charge from the spherical region, from this portion. So now, because of this cavity, this charge will lost its spherical symmetry. Charge will lose its loss its spherical symmetry. If the charge is spherical, this charge if this charge loss its spherical symmetry, then we cannot calculate electric field using Gauss law. Using Gauss law, we cannot directly using Gauss law, we cannot electric field in this case, because as soon as you will create this spherical cavity, the charge will lose its spherical symmetry. Lost spherical symmetry. So now if the charge loses its spherical symmetry, then in this case we cannot directly use Gauss law, then we have to solve in a different way. Okay. So we'll learn how to calculate electric field for this type of situations, but before that, right here, electric field in the cavity, we want to interest electric field, we want to calculate electric field inside the cavity, which is inside a uniformly charge carrying sphere. Uniformly charge carrying sphere. Okay, so we want to calculate electric field inside the cavity, and where is the cavity? Cavity is inside the uniformly charge carrying sphere. So as we have shown in the figure actually, so we have a r radius solid charge carrying uniformly charge carrying sphere, and within this sphere we have created a spherical cavity. The center is at O dash point, and we want to calculate at any point inside this. We want to calculate electric field at any point inside this cavity. So as I already told that in this case, as soon as you will created this spherical symmetry, this charge has no more spherical symmetry. As soon as you will create this spherical cavity, this charge will no more have a spherical symmetry. and because of that we cannot use, or we directly cannot use the Gauss law. So what we have to do then? So if we want to calculate electric field, we have to use Coulomb's law. But again, I mean, calculating electric field using Coulomb's law will be always not a good option. I mean, you have to do some time of, in this case, volume integral, and for any arbitrary point, this volume integral will be a little bit difficult. So for this type of situation, what we can do, again, we can use a Gauss law, but in a different way. Gauss law in a different way. So if I ask you, or if I just think this system in this way, let's say there is no cavity. So when I say there is no cavity, that's mean we have a uniformly charged carrying sphere. So we have a uniformly charged carrying sphere. So let me just draw these two situations together. Let's say we have a uniformly charged carrying sphere. The center is at O, and this sphere is carrying a uniformly charged. Like this. Okay, so this is the case when there is no cavity. No cavity. This is the R radius sphere, and this center of the sphere is at O. At O. Now, just consider only this cavity portion. I'm adding a plus sign here. Later we'll think about it. Just draw this spherical portion only. Spherical portion whose center is at O dash. And assume that this charge is also, this cavity portion is also carries a uniform charge density, but in this case it's a negative sign, minus rho naught. Okay, minus rho naught. O dash point, and this is carrying minus rho naught. Okay. So we have to calculate electric field for this case, where we have a uniform charge carrying sphere, and inside this uniform charge carrying sphere we have to make a spherical cavity. That's mean in this cavity region there is no charge. Okay. So if we want to calculate electric field inside the cavity, so in this case we cannot use directly Gauss law, because of this cavity, this charge distributions has no more spherical symmetry. So in this case, we can calculate electric field within this cavity in this way. So first step, if we assume that there is no cavity, then we will see a uniformly charged carrying sphere of radius r like this. Uniformly charged carrying sphere like this. And then if we consider only this cavity portion, and then if we superpose these two sphere, what will happen? When we assume that there is no cavity, that's mean in this cavity portion, we have already assumed that there are some positive charge of density rho naught. Density rho naught. Now, if we consider only this cavity portion with a negative charge density, and then if we superpose these two, then what will happen? Already there have some positive charge and same amount of negative charge. If I put here, then positive charge, negative charge, they will just neutral their effect. So eventually these portions will be empty. So there will be no charge. So superposition of these two situations give you the original charge distribution. Superposition of these two situations will give you the original charge distribution. And what will be the benefit of doing this? Now, if we consider one situation at a time, if we consider only this situation, then we can calculate what will be the electric field inside the cavity region. Let's say this is the center of the cavity. So if I consider a point P, let's say the point P, this point is P. So you can say that this point is P. So if we want to calculate the electric field at point P, what we have to do, we have to simply, it will connect with the O, and we can calculate what will be the electric field at this point. Because now we are considering this, there is no cavity, then this point will be lies in inside a, this point will lie inside a uniformly charged carrying sphere, and we already know how to calculate electric field inside a uniformly charged carrying sphere. It will be rho naught r divided by 3 epsilon naught r cap, it is positive charge. And then if we consider only cavity portion, then also, since cavity portions also we are considering this way, okay, this is also a spherical part and a spherical charge carrying sphere, but in this case charge density is minus rho naught. Charge density is minus rho naught. So again we can calculate what will be the electric field at this point. At the center is O prime, and inside a point we have to consider a point P. Let's say this point is P. We can calculate what will be the electric field at this point P. And then if we superpose these two charges, we'll get the final original charge distribution. So according to superposition principle, we can say that the net electric field at any point inside the cavity will be the superposition of these two cases. Whatever we'll calculate at point P due to this case, whatever we'll calculate electric field at point P due to this case, if we added these two electric field according to law of vector, I mean using the vector law of adding two vectors, we can calculate, we will get the final electric field at this point. Okay, so break down this situations into two different situations. Actually we can easily calculate the electric field using the standard result, what will be the electric field inside a uniformly charged carrying sphere. So I mean we can calculate this electric field using either Coulomb's law, but if in this case if we want to calculate using Coulomb's law, then we have to do a different difficult integration, which will not be so easy. You can try to calculate electric field using Gauss law within this cavity. I hope it will not be, this integration will be very difficult. So in order to avoid this difficult integration, what we can do, we can just break down these situations, ideal conditions into two different situations. In one situation we are assuming that there is no cavity, then we will see the uniform charge carrying sphere, so we can calculate whatever the electric field at point P. And then next step we'll consider only cavity portion, but with a charge density minus rho, so it will also behave like a charge carrying, uniformly charge carrying sphere with a charge density minus rho. So we can calculate what will be the electric field at point P, and then if we superpose these two, we'll get the final electric field. Okay, then do it in this way. We want to calculate electric field. So what we have done here, this is the center of the sphere O, and this is the center of the cavity O dash, and this is a point P, arbitrary point P. We want to calculate electric field. So let me just draw these 2-3 points together. Let's say connect this O point with O, and then P point, and then O dash P point. So let me draw a bigger picture here. We have O dash point, we have O point, and we have P point. O point, O dash P, and OP. O dash O and P. So this is O dash vector, O dash P vector, and this will give you OP vector. Okay. So now just write it two different cases. So case one, consider there is no cavity. Consider there is no cavity. Okay, there is no cavity. If there is no cavity, then what will be the electric field at point P? So this is the point P. If I want to calculate at this point, so then electric field at point P can be written as, or we can write this electric field at point P, since this point is inside a uniformly charged carrying sphere, and if this distance is r, I mean the distance of p point from the O point, then we can write electric field is equals to rho naught r divided by 3 epsilon naught into r cap, into r cap. And then if we multiply this r cap into r, what we'll get actually r vector, that is the position vector of the point P with respect to the center of the sphere. And this also we can represent by OP vector, OP vector. So we can simply write this in terms of OP vector. So it will be rho naught and then OP vector divided by 3 epsilon naught, 3 epsilon naught. So that is the electric field at point P when we consider there is no cavity. And let me write it in this way. This is electric field in case 1, so E1. Okay, E1. Now case second, where we have assumed only the cavity portion. So case 2, consider only cavity portion, with volume charge density rho is equals to minus rho naught. Rho is equals to minus rho naught. So now consider this sphere. This is also a sphere, and in this case this is also carries a uniform charge density. Only this charge density is now negative, right? And this P point is also within this cavity. That's mean in this case it will be inside a uniformly charged carrying sphere. So then electric field at point P can be written as, let's say write it in terms of, let's say 2. So E2 is the electric field at point P because of due to only this cavity portion which is carrying a negative charge density rho naught. What will be that electric field? Since it is also a uniformly charged carrying sphere and then P point is lies within the uniform charge carrying sphere, so again we can use the same result here. So it will be, if it is positive charge, then it will be rho, and then at point P we have written as OP vector. So at this point it is a P, but with respect to the center of the cavity, that is O dash. So we can write O dash P divided by 3 epsilon naught. And then if the electric field will be along O dash P when the charge is positive, but in this case within this cavity we have considered the negative charge density, so because of that there will be a negative sign. Yeah, so this is the electric field at point P. But the situation is not like that there is only uniform charge carrying sphere or only cavity. If we superpose these two together, then only we will get the original charge distribution. So if we want to calculate electric field at point P within this cavity, net electric field at point P inside this cavity, and cavity is inside a charge carrying sphere, then what we have to do, we have to superpose these two charge distribution. When you superpose these two charge distribution, then only you get the net electric field at point P. So according to superposition principle, we can say the net electric field at point P will be the vector sum of these two electric field. Vector sum of these two electric field. So right here, next page, right here, according to superposition principle, superposition principle, the net electric field, the net electric field the net electric field at point P is E is equals to E1 plus E2. Okay, E1 plus E2. So now what is the value of E1? E1 is rho naught OP vector divided by 3 epsilon naught. And what is the value of E2? It is minus rho naught O dash P vector divided by 3 epsilon naught. Divided by 3 epsilon naught. And then if we take rho naught by 3 epsilon naught common, then what we'll get? We'll get OP vector minus O dash P vector. Minus O dash P vector. And then we have drawn a figure here. Let me just draw in this way. We have a O dash point here, that is the center of the cavity. We have a center of the charge carrying sphere, that is O, and inside the cavity we have considered a point, arbitrary point P. So this is the O dash vector, this is the O dash P vector, and this is OP vector. So from this figure, what we can write? We can write O dash plus O dash P is equals to OP vector. Is equals to OP vector. So what will be the value of OP minus O dash P vector? So if we write O dash vector is equals to, can write OP vector minus O dash P vector. So if we replace this value here, then finally what we'll get? We'll get rho naught divided by 3 epsilon naught O dash vector. O dash vector. So that's mean the electric field inside the cavity, we have considered a arbitrary point inside the cavity. You say P point can be anywhere in this cavity, but the final electric field at point inside the cavity at any point P, it doesn't depend on the position of the cavity inside the position of the P point inside the cavity. It will be depends on only the center of the cavity and the center of the sphere, the distance between center of the cavity and the center of the sphere, but it will not depends on P. So if we consider any arbitrary point inside this cavity, the electric field at any point inside the cavity will be rho naught divided by 3 epsilon naught O dash. So once we fix this center of the cavity, so we have a charge carrying sphere like this, and then we have a cavity like this. So we have a center of a charge carrying sphere O, then we have a cavity whose center is O dash, and then if we consider any point inside this cavity, let's say this point, either P point could be this point, this point, this point, this point, any point, everywhere this electric field will be, magnitude of this electric field will be O dash, rho by 3 epsilon naught, and the distance between this O and O dash, O and O dash. So it will be independent of position of P within the cavity. So that's mean this suggests that the inside this cavity, in this case electric field will be uniform, and the directions of this electric field will be always, if this, I mean in other region, if you have a positive charge density, then this directions of electric field within this cavity will be along the line O dash, along the line O dash. Okay, if this is the situation, then inside this cavity at any point electric field will be everywhere, magnitude will be same. If you consider any point here or here, everywhere this you see magnitude will be rho divided by 3 epsilon and the distance between O dash, and then magnitude will also be along the direction of O dash, along the directions of O dash. So if I draw like this way, so electric field will be always like along this direction O dash. and since magnitude is same, so we can represent a parallel line. So in this case, inside the cavity, electric field will be uniform. Directions and magnitude both will be always fixed. Directions will be along the line of O dash, center of the cavity, center of the sphere, and the center of the cavity in this direction. And the magnitude will be rho naught divided by 3 epsilon naught O, the distance between the center of the sphere. Center of the sphere. So in this case, if I write the distance between these two cavity and the center of the cavity and center of the sphere is d, so electric field will be rho naught d divided by 3 epsilon naught. That will be the magnitude, and directions will be along O dash. Along O dash. So what we can write about the electric field inside the cavity? This will be uniform electric field. So inside the cavity, electric field will be uniform. So in this case, electric field E will be uniform. Where? Only inside the cavity, not outside. Inside the cavity, electric field will be uniform. Magnitude and directions at every point in the cavity will be fixed. Okay, and if we want to calculate any outside point outside the cavity, let's say here or here, any point, then what we have to do? Again, we can divide it into this way. Now, in case, let's say we have to calculate electric field here. Then what we have to do? First, we'll calculate electric field because of this at this point. So we will use this concept. We have a uniformly charged carrying sphere, and we want to calculate electric field outside this point. So this will be the radius of the spherical surface, and this will be the distance of the point from the center of the charge carrying sphere. Center of the charge carrying sphere. So we'll calculate electric field here, and then we have to consider only cavity portion, only this cavity portion. And first we have to calculate the distance of this point where we want to calculate electric field from the center of the cavity, and then we have to calculate electric field using this definition. So in this case, R will be the distance of the point from the center of the cavity. It will be mentioned in the questions. And also now this radius will be replaced by the radius of the cavity. If you want to calculate electric field only this charge, only cavity portion, then you have to replace in this definition. In this definition, you have to replace this R by the radius of the cavity. So if you do that, then you will get the electric field for two different situations. And then if you want to get the original charge distribution, you have to superpose these two situations. So if you want to calculate the net electric field here, so you have to superpose of these two electric field. You have to take the vector sum of these two electric field, and that will be the net electric field at this point. Okay, so since we have to take a vector sum of these two electric field, so mainly examiner give you some symmetric point where the electric field of this cavity, and because of this surface, they will make either opposite to each other or some particular angle that you can understand easily from the figure, maybe 45 degree or 60 degree, something like this, just because of easily, so that you can easily calculate the electric field. Okay, so I hope you get the idea what is spherical symmetric charge distribution, how we can check the given charge distributions as spherical symmetric or not. If it is spherical symmetric, then either it will only function, it will be constant, or it will be only function of R. It cannot be function of theta and phi. And from there, you also get the idea why this spherical symmetry make our calculation easy in order to calculate electric field for symmetric charge continuous charge distribution. And then using this concept, we have calculated electric field inside and outside due to a uniformly charged carrying sphere, uniformly charged carrying thin spherical shell. And then if we have a thick spherical shell, we have also calculated electric field inside different region. Inside the region where R is less than R1, between R1 and R2, and outside the region that is R2 greater than R is greater than R2. And finally, we have also calculated, we have learned how to calculate electric field inside a cavity, where if we make this cavity inside a uniformly charged carrying sphere. So the concept is pretty clear. When there is no cavity, this charge is spherical symmetric, but as soon as you will make this cavity, it will lose its symmetry. So in this case you cannot directly use Gauss law. So for that, what we can do, you can consider two different situations. In first case, we are considering that there is no charge, no cavity, then it will behave like as a uniformly charge carrying sphere. So you can calculate electric field at any point inside the cavity, that is P point, which lies in this case inside the charge carrying sphere. And then next step, you have to consider only cavity portion but with the opposite charge density. In this case, if it is charge density rho, then you have to check a minus rho. And then you can calculate what will be the electric field at point P because of this cavity portion only. And then since when you take the superposition of these two situations, you will get the final charge distribution, the given charge distribution. So according to superposition principle, if I want to calculate the net electric field at point P, then what you have to do, you have to take the vector sum of these two electric field. So after taking the vector sum of these two electric field, what we get, we have noticed that the electric field inside the cavity will be constant, the uniform electric field. At any point inside the cavity, electric field will be only the magnitude of electric field will be only that only depends on the distance of the center of the cavity from the center of the charge carrying sphere. Charge carrying sphere, and directions will be always along the line O dash. O dash. Okay. So in next class we'll talk about spherical symmetric charge distribution and plane symmetric charge distribution, and then using this result, whatever we have solved today, and then whatever we will solve in next class, based on that we'll also solve few. One day we'll take only tutorial class, that day we'll solve different type of numerical problem based on this result. And then most probably this Sunday or maybe weekdays, I will upload the test related to the electric field calculation and the coordinate system. That's when whatever we have discussed so far. We have discussed a coordinate system. We have also discussed curl, gradient, divergence in different coordinate system, and then we have learned Coulomb's law, and then how to calculate electric field using Coulomb's law for asymmetric charge distribution. Now we have started learning how to calculate electric field due to symmetric charge distribution. So today we have complete one symmetric cases where we have considered spherical symmetric cases and spherical symmetric case, and we have calculated electric field for different spherical symmetric charge distribution. Next class we will learn how to calculate electric field for cylindrical symmetric and plane symmetric, and then one day we'll take a tutorial class based on how to calculate electric field for symmetric as well as asymmetric charge distribution, and then you have to take the test. Okay, so thank you for watching. We'll see you in the next video.